Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afiq Bizabiti and my matric number is AE190063. Now I'm going to present the introduction part of this project. The PID controller is an instrument used in industrial control application to regulate the temperature, flow, pressure, speed and other process variables. This controller uses a control loop feedback mechanism to control the process variable, as this controller also the most accurate and stable controller. PID controller also use the closed loop control feedback to keep the actual output from the process as close as to the target or set point as possible. In this PID block diagram, closed loop system like PID controller include a feedback control system and provide good result compared to the on-off type controller. Next, I'm going to present the literature review. The closed loop speed control system is developed based on the microcontroller. This system is applicable for different size of motor and precisely control the speed of the motor. Next is tuning rule. This method is originally based on controller parameter. They use tangent method to determine the parameter. Another tuning rule can be named as ultimate cycling tuning rule, which can be formed by gains of controller and period at ultimate frequency. The generic algorithm method is used for speed control of DC motor and it consists of three stages like selection, crossover and mutation. For Jaya Optimization Algorithm or JOA, this system is used for speed control of the DC motor. The JOA method can reduce the disadvantage of the traditional method, and the method is simple and not require specific dependent, because this method algorithm is repeated until we get the best value of the parameter. For fuzzy neural method, it consists of four types, which is fusification, fuzzy interference system, rule-based and diffusification. The fuzzy PID controller used to control the brushless motor, and this method is a logical mathematical procedure based on if-then rule system. The last part that I'm going to present is the problem elaboration. The group must follow this procedure in order to achieve all the objectives. The first step is we need to design the block diagram that satisfy the requirement given. An electromechanical system is applied as an actuator in a control system for driving the blade. The next step is we need to derive the mathematical block diagram or motor blade as the load and explain the solved problem using the control system theory, technique and concept. Next, we need to use the MATLAB Simulink to create and run the block diagram to get the result. Lastly, we must fill the table given in the instruction with the value from the result of the manual and auto tuning simulation. That's all for my part. Thank you, and I'm going to pass the presentation to the next presenter.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amir Hakimi bin Zarawi and my metric number is DE200121. So now I will present about problem execution and result. This is mathematical modeling. For DC circuit equation is VA minus RA, RA IA S and minus LA multiplied by IA S minus ES equal to 0. This is for the first equation, and where the ES is the back of EMF. Since back EMF, ES is directly proportional to the angular velocity of the motor. ES equal to KBS delta S. This is for equation number 2. And since torque is directly proportional to the current, TS equal to KA IAS, and this is for equation number 3. Then substitute equation 2 into 3 substitute equation 2 and 3 into 1, which is VAS minus IA bracket RA minus SLA S minus ES equal to 0, and then we can get VAS minus TS over KA multiplied by bracket RA minus SLAS minus by KBS theta S equal to 0. Thus, we will get VAS equal to T bracket RA plus SLA S plus KB KAS theta S over KA, and this is for equation number 4. Since moment of inertia and viscous friction is given, T equal to J d theta d squared theta over dt squared plus b d theta over dt. Then convert to frequency domain, which is Ts equal to Js squared theta s plus Bs theta s, and this is for equation number 5. After that, substitute equation 5 into equation 4. Then we will get VAS equal to Js squared theta s plus Bs theta s bracket and multiply by bracket RA plus SLA S plus KBKAS theta S over KA, and this is for equation number 6. And then to find total moment of inertia and viscous friction, J equal to 0.222 plus 0.022 equal to 0.244 kilogram meter squared. And then for B equal to 0.003 plus 0.0005 equal to 0.0035 Newton ms radius negative 1. After that, the transfer function is theta over VA equal to theta over bracket Js squared theta s plus Bs theta s bracket RA plus SLAS plus KB KAS theta S over KA, and then we will get theta over VA equal to KA over LAJ multiplied by S cube plus RAJ plus LAB squared plus KA KB plus RABS, and then we will get like this. After we substitute this below, we will get theta over VA equal to 1.28 over 0.0295 S cube plus 2.7332 S squared plus 1.6392 S. And this is a mathematical equation that we get. And this is for the block diagram that we use in this assignment and in this project. And this is for mathematical equation or mathematical model for transfer function, which is this is a step and this is a transfer function, and this is scope. This is a response of system at 500 RPM, and this is the result, the graph result for response of system at 1500 rotate per minute. For the PID controller, is set to 0, while integral and derivatives is set to 1. The step input is constant at 500 RPM, then which we will change to the higher RPM, which is 1500 rotate per minute. The graph output can be seen by running the circuit, and this is the block diagram for with the controller. Okay, as you can see here, this is the circuit that I made in Simulink in lab, which is this. If you want to find P, we will click this block, and we change it to P. Okay, and this we will set to 1. And then we click OK. So this is step, and for the proportional gain, for the PID controller, we will set P and set to the 1. And this is for the mathematical equation that we get after we calculate in the previous I showed. After we set P equal to 1, Kp equal to 1, and we will get the graph like this. The proportional gain Kp is increased until neutral stability is achieved. Since the relative gain Kd and integral gain Ki is set to 0, the critical gain at neutral stability Kc is equal to proportional gain. And the Kc that we obtain in this explanation is 116.77, which is after we set Kp equal to 116.77, we will get the graph like this. After applying Kc and Tc, we obtain the manual PID tuning chart shown in the table 1, which is P equal to 58.385, Pi equal to 52. Kp, for the P we will get 58.385, and for the P for Pi we will get 52.5465, and PD we will get 93.416, and for the PID we will get 70.062, and for the I for P we will get no, and for the Pi we will get 0.71, and for the PID we will get 0.426, and for the TD which is for PD we will get 0.1065, and for the PID we will get 0.10652. Okay, for the controller, this is the formula that we will use to find the Kp, which is Kp equal to 0.5 multiplied by Kc, and as you can see here, 0.5 multiplied by Kc, which is 116.77, which is we will get 58.385, which is this is we will get P. And for the controller Pi, we also use formula 0.45 multiplied by Kc, and then we will get like this, which is 52.5465. And for the Ti we will get for the Ti we will use a formula which is Tc over 1.2, which is 0.852, over 1.2, which is we will get 0.71. For the controller PD, the formula that we use is 0.8 multiplied by Kc, and we will get 93.416. And for the TD, we will get the formula that we use is Tc over 8, which is we will get 0.1065. And for the controller PID, for the Kp, we use the formula 0.6 multiplied by Kc, and we will get 70.062. And for the Ti, Tc over 2, which is we will get 0.426. And for the TD, Tc over 8, we will get 0.1065. So this is the table 2, which is proportional, integral, and derivative gain, which is manual. Okay, this is the calculation that we get for using formula Ki equal to Kp over Ti, and Kd equal to Td multiplied by Kp. And for the Pi controller, we will get 74.009, And for the PD controller, we will get 9.9488. And for the PID controller, we will get 164.4648. And for the KD, we will get 7.4616. This is the manual tuning that we get from the simulation that we run. When the system responds at 500 for the P, this is the graph that we get, and this is system response at 1500 RPM, and this is the graph that we get. And also for the PI, this is for 500 RPM, and this is for 1500 RPM. As we can see here, the graph is a little bit different, which is this is more peak, and this is less peak. And for the PD, this is the graph for 500 RPM, which is, as we can see here, this is the small peak. And for the 1500 RPM, for the graph, you will get a little bit big peak. And this is for the PID at 500 RPM. This is the graph. As we can see, it's a little bit smaller than one from the response 1500 RPM. And this is for the manual tuning, and this is for the automatic tuning. The system response at 500 RPM. This is the graph that we get. For the 1500 RPM, this is the graph that we get, and this is a little bit higher than 500. And for the PI, for the auto tuning, automatic tuning, for the 500 RPM, we will get also like this, a little bit lower than 1500 RPM. And for the PD, also same. For the 500 is a little bit lower than 1500. And also the PID also same. So for the deficits, is proportional, integral, and derivative gain for the automatic tuning. As we can see here, this is the data that we get. Okay, let me show you for the data that we get. I'm sorry, this is a little bit problem in my software simulation. But as we can see here, this is the automatic for the system response. As we can see here, this is the graph for the P control type, and this is for the controller parameter, and this is for the PI, and this is the controller parameter. And for the PD, also the same. This is the graph for the PD, and this is the graph for the PID tuner. And here is the comparison between manual and auto tuning. For the tuning method for KP, for the manual we will get 70.0620, and for the automatic we will get 1.58720277774734. And for the KI, KI tuning method, for the manual we will get 164.4648, and for the automatic, the data that we get is 0.229692868521888. And for the KD, for the manual tuning, we get 7.4616, and for the automatic tuning we will get 2.03650634982024. And this is the comparison between manual tuning and automatic tuning. The difference in gain is due to the filter coefficient, which is unchanged by the automatic tuning method, but in the manual method, the filter coefficient is not changed and set as constant 100. So this is the diagram for filter coefficient and of automatic tuning method. And for the input versus manual tuning, also versus automatic system response. This is the input speed for 500 RPM, and this is for 1500 RPM, which is this is without controller. As we can see the graph here, it is a little bit almost same, and for the manual also almost same, but for the 500 RPM it's a little bit lower than 1500 RPM, and for the automatic the graph also for the 500 is little bit lower than 1500 RPM. So for the conclusion, the controller will support manual PID tuning, which means the P, I, and D variable must be calculated manually by the engineer and set via the controller menu. To be able to perform the calculation, the user must have a reasonable degree of knowledge and understanding. Manual PID tuning frequently necessitates from some trial and error testing to obtain maximum efficiency. When compared to the alternative, manual tuning might be exceedingly time intensive. The auto-tuning, also known as self-tuning of PID setting, is supported by majority of current PID process controller. The method this work depends on manufacturer product, but they often employ the rule-based computation in the same manner, and then as an expert engineering tuning the device manually. To conclude this project, when adjusting the manual tune parameters, it is discovered that using the try and error method can result in enhanced system stability, which fewer overshot and more noticeable acceptable setting time when compared to the auto tuning method. So that's all for me. Thank you.